Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through phases and phasor diagrams. In our previous lesson, we saw that in AC or in AV, the voltages and the currents may not be in phase. So the representation is a little bit unusual. Because of that, to account for the representation of the phase difference, we use what we call a phases, or we call it phasor, right? Or a phasor diagram. So a phasor is nothing but a vector representation of a voltage or a current. So I write my V and I'll show the direction. I write my I and I'll show the direction, right? So the purpose of phasors is to show clearly the phase difference for a voltage or current or two quantities. You realize that in DC, because our current and voltage are in the same phase, I have my voltage and my current. There is no need for phasor diagrams. But when the current and the voltage are out of phase, you realize that you have your voltage here and your current here. Therefore, they will be separated at a phase angle of phi or theta, right? So this is what we call phases. So you should understand the use of phases and how we can represent phases. Okay, so now let's see this nice scenario. I have a phasor V here, which is V2, right? Which is separated from the vertical by 60 degrees. I have another phasor V1 which is vertical. Right now, the problem is, what is the phase difference between V1 and V2? So in AC theory, phases are not necessarily always together or in touch. They can be separated, but you should be able to find the phase difference between these two. This arrow is pointing down, but separated from, the angle with the vertical is 60 degrees. So these two are separated by phase difference. But what is the phase difference? To do this, let's see something here. I introduce an imaginary dash using the planes angles here becomes 60, right? So this one is a perfect representation of the V1. You can see because the V1 is a vertical one, right? So realize that our V2 needs to go anti-clockwise 120 degrees in order to assume the shape of V1, or in order to be in phase with the V1. Therefore, we say that the phase difference phi is equal to 120. As simple as that. Or the V2 is lagging by 120 degrees. Having talked about phases, let's analyze some phasor diagrams problems here, right? So let's take a problem here. So it says that a 50 hertz source, right? So a 50 hertz source have RMS voltage of 240 volts, delivers RMS current of 10 amperes to a circuit. The current lags the voltage by 30 degrees. A. Draw the phasor diagram. Then B. Express the voltage and current as functions of time. So this is a nice problem here. It said a 50 hertz source have an RMS voltage of 240 volts and delivers RMS current of 10 amps to a circuit. The current lags the voltage by 30 degrees. Draw a phasor diagram and express the voltage and the current as functions of time. So here, the first part is to draw a phasor diagram for what has been described here. Okay, so for the solution, our f is equal to 50 hertz. You put it down, your parameters first. Then Our voltage is equal to 240. Current I is 10 amps. You realize that they are saying that the current lags the voltage by 30. So if you choose to represent the voltage as a horizontal V, then the current will lie here with an angle of 30 degrees. Okay, so I, as simple as that. So this now becomes the phasor diagram. It's not anything conventional, anything specific or standard. Just make sure that the difference is shown to everyone, that the current is lagging the voltage by 30 degrees. Now for the B part, you have to express the voltage and the current as functions of time. What they are trying to say is, let's express it in the standard form, a form where it represents the wave equation. You have your frequency. All we need is to find our, what do we say, angular frequency. So angular frequency omega is simply equal to what? 2 pi f. So 2 pi times our frequency 50 will give us 100 pi. As simple as that. Now we'll just look at for the peak. So here they give us the RMS voltages. We need the peak voltages. We don't need the RMS to write the wave equation. So we need a peak. So peak voltage or current is simply equal to the RMS value times square root of 2, as simple as that. So to represent the 240 voltage, I'll have my V to be equal to 240 square root of 2, right? That is my peak voltage. Sine 2, now it's 100 pi, right? So sine 100 pi t, as simple as that. My current I becomes what? My current is 10 amps, right? So 10 root 2 sine 100 pi t, as simple as that. So this is how you can represent your voltage and your current as a function of time. Now let's talk about addition and subtraction of phase diagrams. So addition and subtraction of phasor diagram. So whenever you have a phasor diagrams, you can add or subtract, right? So how do you do that? Let's use this example to understand that. So I have V1, a function of t to be equal to 60 sine omega t. And I have V2, a function of t to be equal to 80 sine wt minus 90 degrees. The problem is determine A, V1 plus V2, then B, V1 minus V. So we are trying to add and subtract phases. How do we do that? So for V1, you realize that it doesn't have any phase difference attached. So the phase difference is 0. So the V1 simply attains a horizontal shape. Okay, take note of that. So we just use a horizontal shape for V1. V2 is 80 sine. So 80 is the peak voltage, but it is lagging V1 by 90 degrees. So it's a perfect 90 degrees. So to come down, it's lagging. Now, so this is V2. Okay. Then now we have to find A, V1 plus V2. Please, these are vector quantities. Whenever you want to add them, we use the vector approach. So the vector approach, we have V1 plus V2 in the middle, where the angle here becomes our phase difference for the entire summation. Okay, this is one approach in solving this problem. So look at it. So this is when you are using the vector approach to solve this problem. You know that your V2 is what? 80, your V1 is what? 60. Find the magnitude of this. Remember, we use a Pythagoras theorem because this is a right angle triangle. So here is V1 plus V2. My horizontal is what? V1. Vertical is V2. To find my V1 plus V2, the magnitude is simply equal to the square root of the expression V1 squared plus V2 squared. And that is square root of 60 squared plus 80 squared, giving me what? 100. As simple as that. Right. So once you have 100 there, then the next one is to find the theta. So theta now here is equal to tan inverse, because check, tan inverse of the vertical, which is V2, and V2 is 80 over what? 6. Is that not it? 80 over 60. So what's the answer? So tan inverse of, so that is 53 degrees, 53.1 degrees. So here we have our value, here we have our phase. So simply v1 plus v2 equal to 100 sine omega t minus 53.1. This is because we follow the phase difference shown. We realize that v2 is lagging, so their sum is not going to lead, right? The sum is 53. So we realize that it was lagging by 90. But when I combine the two, it has reduced, meaning it's getting closer. Okay. Now, the second one says V1 minus V2. What it means is we are supposed to invert V2, negative of V2. So here, if V2 is pointing down, then it means that if you want to negate it, it should point up. And how do we do that? We need to rotate it through 180 degrees. So you are going to have V2, which is originally 80 sine WT minus 90 plus 180 degrees. Rotate it in 180. This gives 80 sine WT plus 90 degrees. So this then changes the orientation so that you have V2 now pointing up, then still V1 the horizontal direction. Then we have the negative V2 plus V1 here, then the angle theta, which is the phase difference. So here the magnitude of V1 minus V2 will obviously be the same as 100, right? So the magnitude is the same, but let's see for the so the magnitude is still a square, because when I take this I have v1 base v2 here, so it's a square, so magnitude is simply equal to 100. The angle is also the same, tan inverse of what? Theta is now equal to tan inverse of my v2 over v1, which is also equal to 50. But here the difference is that we are now leading. The v2 is now leading, so our phase difference now is going to what? Is still going to lead. So the answer is rather 100 sine wt plus 53, so plus 53.1, simple as that. So yes, this is the end for Phasors and Phasor diagram. More problems will be solved as we move along the course. So do well to subscribe and also to share as well.